Hi everyone, this is Orion. Today we're going to be doing a classic fluid dynamics problem that we have. We have these two tubes that are, or I guess we have one huge tube that's connected at a U-bend, and we have two different fluids with different densities given. We have water and mercury. So this is a pretty tricky problem. It's a classic textbook problem that they love to throw, especially university students, under the bus with. So we'll tackle this problem together and see how we can dissect it. So the first thing to do, because we're dealing with a lot of different heights, we're given that the height between the mercury on both sides is about um, 0.0196 meters. And so what we can do is we can just draw dotted lines between both sides. Um, and we can label this as H2. We're given H2, and we'll write this as our variable, so we can kind of add that to our givens. We're given the density of water is 1 times 10 to the third pascals, and we are also given that the density of mercury, 13.6 times 10 to the third. Uh, we're, what we want to know, where we're trying to get at, is the difference between the height in the water. Um, and using our information and knowledge about density, about Pascal's law, and all sorts of things, we're going to be trying to solve for H1. That's going to be the destination we try to arrive at. So how do we go about tackling a problem like this? Well, we can use Pascal's law, what we know. The sum of all pressures on one side of a connected system is equal to the sum of all other pressures on the other side. So in addition to we're given that the pressure is atmospheric pressure, so pressure from the air, plus the density, this is in terms of liquids, the density times acceleration due to gravity, and then the height. So it's important that we take into consideration the height and where we're working from. Let's, just for this example, to make things a lot simpler, we can use this height as 0. And essentially, what that does is we're ignoring all the mercury underneath that height. It's irrelevant to us, and at least for the scope of this problem. So this simplifies things quite a bit. We can also make another intermediary height um, called height 3 that we don't know either. And what's nice about this is that because height 3 is involved and it has water on both sides, they'll actually both of those sides on the right side and the left side are equal, and so they'll actually cancel out when we write out our equation. So that makes it pretty nice for us. So let's go ahead and write our big equation using Pascal's law. And of course, we have the atmospheric pressure, right? Um, that constant that we're given. As it turns out, it also cancels on both sides, so we don't even have to write that down. But it's good to know it. They'll probably give it to you on a reference sheet or something. So let's write out our equation. We have P naught plus the density of water times acceleration due to gravity. Let's start with the left side. So for this side, we have um, all this for water, and this goes all the way down to 0. So it's height 1 plus height 2 plus height 3. So we can write that as our height 1 plus height 2 plus height 3. And then we'll see it set it equal to the pressure on the other side because the system is in balance. It's not accelerating. On this side, we also have the atmospheric pressure, and then we can add that to the density of water because right here we have water at height 3. So we can do density of water times acceleration due to gravity, height 3 plus, we also need to focus on this section with mercury. We're given the density of mercury times acceleration due to gravity and height 2. Cool. Now the P naughts cancel on both sides. And we're given, we can also actually, before we even do that, we have a G on both sides. On So what we can do is we can divide all three sides by G and actually cancel out um, all the G's, which is nice. So what that tells us is that acceleration due to gravity doesn't really matter. So if we're on a different planet with the same atmospheric pressure, actually, because the atmospheric pressure canceled out, that doesn't matter either. So that tells us physically we could do this experiment on a different planet, given that the fluid wouldn't start floating or something like that, which is pretty cool. So when we distribute the density of water, we get PW H1 plus, it's actually rho, not P, that's my bad. Rho W H2 plus rho W H3. And then we set it equal to this side, which is rho W H3 plus rho density of mercury times H2. Cool. So essentially what this tells us, we can subtract the density of water times H3 on both sides. And that essentially tells us that this segment right here, um, from about H3, we can not include that in our equation. And it doesn't really matter what H3 is, if it's, 3 meters longer or infinitely shorter, it doesn't really matter, which is pretty cool. So we're left with this equation, the density of water, H1, plus the density of water, H2, equals the density of mercury times H2. Cool. Now we can separate and solve algebraically for H1. So when we do that, we get H1 equals the density of mercury times H2 minus the density of water, H2, all over the density of water. Now, this is a beautiful equation. It's very easy to plug in, and we have our given values. So essentially what we did is we took these different heights, we assigned values to them, we used Pascal's law, did a lot of canceling to simplify this equation, and now when we plug in our values, we can get H1. Hope this helps. I know fluid dynamics can be pretty tricky, but it's not too bad once you boil things down and use the laws that were given. Anyways, thanks for watching. Have a good one.